Okay, let's talk large language models, or LLMs. You hear that acronym everywhere, right? But what are these foundational models really? We're going to do a quick explainer, break down the core ideas behind this AI tech that's seriously changing everything.
And calling it a seismic shift, that's actually not an exaggeration. Seriously, these things are fundamentally changing how we work with computers, how we get information. I mean, they process and even generate language in ways we just haven't seen before. It's a big deal.
So here's what we'll cover. First, the big picture view. Then, we'll peek under the hood at the transformers' secret. After that, how making them bigger changed the game. That's scaling up. Then, how we make them more useful and faster in refining and accelerating. And finally, we'll look at their impact and what might be next. Ready? Let's go.
All right, first up, the big picture. What exactly are we talking about with LLMs, and why should you care?
Okay, so at their heart, LLMs are really sophisticated AI systems. Think deep neural networks, but trained on absolutely enormous piles of text data, like unimaginable amounts. And it's this massive training that lets them pick up on all the patterns, the nuances, the kind of hidden rules of language. That's how they get so good at understanding and even generating text that sounds, well, human.
So why all the fuss? Well, it's a few things hitting all at once. First, they just blow older language processing methods out of the water in terms of performance, like it's a huge jump. This opens the door to all sorts of new applications, really good translation, writing code that actually runs, chatbots you can have decent conversations with, even tackling complex reasoning tasks. Plus, you can take a general model and tweak it, fine-tune it for specific jobs. And you can guide them with just plain text instructions, which we call prompt engineering. That makes them super flexible.
But how do they manage all this? That leads us right into Section 2, uncovering the secret ingredient, the transformer architecture.
See, before transformers came along, models like RNNs, recurrent neural networks, read text one word after another in sequence. Kind of like we do, right? But that made them slow to train because you couldn't easily do things in parallel. And importantly, they often kind of forgot the beginning of a long sentence by the time they got to the end. Transformers, totally different approach. They look at all the words at once, basically. This parallel processing makes them way faster to train. And crucially, they use this cool thing called self-attention to understand how words relate, even if they're far apart in the text. Big improvement for handling context.
So the transformer architecture itself, it landed back in 2017. Originally, it was built for machine translation, using this two-part encoder-decoder setup. But a lot of the big LLMs you hear about today actually use just the decoder part, which turns out to be really good for generating text, like writing or answering questions. But the real star, the absolute key piece of the puzzle, it's that self-attention mechanism. That's the magic.
So what is this self-attention thing? Let's simplify it. Imagine every word in a sentence basically looking around at all the other words and asking, hey, which of you guys are most important for understanding me right here? It's like each word calculates a relevance score for every other word. Based on those scores, it then pays more attention to the meanings, the values of the important words. This lets the model build a really rich context-aware understanding of each word, based on the entire sentence, not just its immediate neighbors. It's how they handle ambiguity and complex relationships so well.
And they didn't stop there. They came up with multi-head attention. Basically, instead of just one attention calculation, the model runs several of these attention heads in parallel. Each head can learn to focus on different types of relationships between words simultaneously. Maybe one looks at syntax, another looks at semantic similarity, and another tracks pronoun references. Doing this all at once gives the model a much deeper, more multifaceted view of the text. Pretty clever, huh?
Okay, so transformers gave us the blueprint, but the next revolution came from just making them bigger, a lot bigger. Section 3, scaling up. This is where things got really interesting.
Just look at this timeline. It's wild how fast things moved. 2018, we get GPT-1 showing the power of pre-training without direct supervision, and BERT cracking bidirectional understanding. Then boom, 2020, GPT-3 arrives, way bigger, and showing off this cool few-shot learning where it could do tasks with just a couple of examples. Then in 2022, Chinchilla gives us key insights into how to scale smart,
Not just bigger models, but more data too. And now we're seeing things like Gemini pushing into multimodal territory, handling images and audio. The acceleration is just incredible.
And when we talk scale, we mean scale. Look at the parameter counts. Think of parameters as kind of like the knobs and dials inside the model, representing its complexity. GPT-1, around 117 million parameters. Seemed huge at the time. Fast forward just a few years, and models like Palm hit 540 billion parameters. Billion with a B. That's almost a 5,000-fold increase. This exponential growth curve is really what defines modern LLMs.
Now, what did all this scaling do? Well, the chinchilla paper dropped a bombshell insight. The best results don't just come from bigger models, but from scaling up both the model size and the training data size together in the right proportions. It's a balancing act. And as models got bigger and were trained optimally, something amazing happened. Emergent abilities. Skills started popping up that the models were never explicitly taught, like being able to perform tasks with zero or just a few examples, zero-shot or few-shot learning. And overall performance just got way better across the board, making them much more generally capable.
So we've got these giant, super smart foundational models. But raw power isn't always useful, right? And they can be slow. So Section 4 is about refining and accelerating, making them practical.
The main way we tailor them is through fine-tuning. You take that big, pre-trained model that knows a lot about language generally, and you keep training it, but this time on a much smaller, specialized dataset. This focuses the model, making it better at a specific job, like following instructions accurately, or help shape its behavior, maybe making it safer, or better at carrying on a helpful conversation.
And there are different ways to fine-tune. There's supervised fine-tuning, or SFT. That's where you show the model lots of examples of, here's the input prompt, and this is the good output you should give. Pretty straightforward. But then there's RLHF, reinforcement learning from human feedback. This one's really interesting. Instead of perfect answers, you have humans look at several different outputs the model generated and rank them. This one's better than that one. The model then learns from these human preferences. This is huge for making models like ChatGPT feel helpful and aligned with what users actually want.
Let's break down that RLHF loop real quick. First, the LLM spits out a few possible answers to a prompt. Then, a human reads them and says, okay, I like answer B best, then A, then C. A separate AI, called a reward model, gets trained to predict those human rankings. Finally, the original LLM gets updated using reinforcement learning, trying to generate answers that the reward model would score highly. It's this continuous loop of generation, human feedback, and model updates that helps steer the LLM towards being more helpful and safe.
Now, fine-tuning these monsters can still cost a lot of compute power. So, clever folks came up with parameter-efficient fine-tuning, or PEFT methods. Techniques like LoRa basically freeze most of the huge model and only train a small number of new parameters. It's way cheaper, but still gets good results. And what about speed? Getting answers fast, that's called inference, is super important. So there are lots of tricks here too. Things like quantization, which uses numbers with less precision to save memory and speed things up, or speculative decoding, where the model kind of makes a quick draft and then checks it, or prefix caching, which avoids recalculating things it's already done. All about getting those responses back to you quicker.
Okay, we've got powerful models, scaled them up, refined them, sped them up. So what's the payoff? Our last section, impact and beyond. What are these things actually doing, and where is this all heading?
Man, the applications are just exploding. Seriously, look at this list. Helping write and debug code, tackling math problems, doing really good translation, summarizing long articles in seconds, answering complex questions, powering those conversational chatbots everyone's talking about, helping with creative writing. And it's not just text anymore. They're increasingly working with images, audio, even video. The range is just nuts, and it grows like every week, it feels like.
I think this quote really nails it. It's not just about replacing things. It's about technology that can assist us, complement our skills, empower us to do more, and maybe even inspire new ideas. And that potential cuts across pretty much any job, any field you can think of. It's about partnership, often. So yeah, the future isn't something way off in the distance. With LLMs, it feels like the future is happening right now. Their abilities are evolving so incredibly fast, which leaves us with the big question, right? How are these foundational models going to keep changing the way we interact with technology, with information, maybe even with each other? It's something we're all going to be figuring out together. Wild times.